Hello, my name is Wolfgang Schweiger. With this presentation I will give you an insight into our research work about gearing pumps or so-called Gerotor pumps. This research work has been done in cooperation with Graz University of Technology in Austria and Maha Fluid Power Research Center of Purdue University in Indiana. There is a wide range of applications for gearing pumps, however, in this presentation we focused on all-wheel drive powertrain applications. Here we see different all-wheel drive systems. They are using gearing pumps with different designs and different operating conditions. As you can see, there are different requirements and we can basically define these three categories of pumps used in automotive drivetrain systems. Here we see some more pump designs which differs in the dimensions, in the number of Ds and their specific Ds shape. The motivation of our work and the research goal can be summarized as follows. To develop a computational multi-domain simulation methodology for gearing pumps which is suitable for the pump design and for concept considerations in an early stage of development without having detailed CAD data available. The model should consider the mechanical and hydraulic effects as well as the pump tolerances and their interactions, and in that way an accurate prediction of the system behavior in the course of a complete system simulation should be enabled. In literature, many papers can be found dealing with specific aspects of the pump design, but there is no clear answer for a comprehensive system simulation in a high level of detail. Here is just an overview to show the most important works, and I will refer to the literature overview in the paper. Rather, I will give you now a brief explanation of the gearing pump operating principle and their main components. Therefore, the particular case of an electrohydraulic actuated coupling has been chosen. The coupling provides torque control between the front and the rear axle of a vehicle with a wet multiplate clutch. The transfer to torque is nearly proportional to the pressure acting on the clutch piston. The pump is driven by an electric motor and the hydraulic pressure is built up to actuate the piston. But let us now focus on the pump. The gearing pump is a positive displacement unit consisting of a rotor set with an inner and outer rotor, and the axles have a fixed center of rotation and a fixed eccentricity. There is a housing comprising usually three parts: base plate, a mid plate and a cover plate which contains the suction and the delivery ports. The pump works in the following way. The inner and outer gears are rotating at their respective axes. Due to the eccentricity and the difference of number of Ds of one, displacement chambers composed of inner and outer rotor Ds geometry are formed. The motion causes the displacement chambers to suck in fluid at the suction port and to displace it into the delivery port. The rotor set is radially supported in the housing in a hydrodynamic lubricated bearing and axially supported by the end plates which composes the lateral sealing gaps to the rotating kit. These interfaces have been considered by the proposed simulation approach and will be explained in more detail later. Let me now explain the developed modeling approach. It comprises models for geometric generation, calculation of required geometry data, a 3D geometry model, furthermore a FEM and CFD model, and a lambda parameter fluid dynamic model which contains a model for the hydrodynamic lubricated outer rotor bearing. Additionally, there is a pump database and the geometry import-export facility included. As you can see, there are different simulation platforms involved and the models and their interactions are controlled by a global graphical user interface. Furthermore, the pump model, following this modeling approach, can be extended by any hydraulic circuit. Dynamic system simulations can be performed and the interactions when the pump is working in a complete hydraulic circuit can be analyzed. Now I want to explain the respective models. The geometric model generates the gear profiles based on trochoidal curves and their envelopes. A trochoidal curve is traced by a point A that is rigidly connected to a circle, which is rolling without sliding along the inner or outer circumference of another circle. This creates a basis trochoidal curve, but this curve contains unwanted spikes and it cannot be used as a rotor profile. So an equidistant curve with the offset radius ρ is generated by point C, and this is our first rotor profile. The second rotor is obtained as its conjugate and has one more Ds than the inner rotor. So each tooth of the inner element is in continuous sliding contact with the surface of the outer element. And in the model I use the minimum number of parameters to represent any Gerotor profile. Let me now come to the fluid dynamic model. It evaluates the flow through the gearing pump and is the central part of the simulation procedure. After creating the gear profiles, we can consider one displacement chamber as an equivalent piston which is connected to the inlet and delivery ports with equivalent orifices. Additional orifices are considering the internal and external leakage passes. For each chamber, the pressure build-up equation is solved. For the inlet and outlet orifices, the equation for turbulent flow is used. For the leakage passes, the equation for laminar flow is used. Currently, we are working on the CFD model to evaluate the leakage flow in the lateral sealing gaps. It will be explained later. Then there is a second geometric model which calculates all geometric parameters required by the fluid dynamic model as a function of the angular position of the gears. In particular, the model computates the area of one displacement chamber and the intersection zone between the displacement chamber and the inlet port, and the intersection zone between the displacement chamber and the delivery port, and this is shown as shaded area in this animation. This is how the fluid dynamic model looks like in the emisim environment. It is based on the lumped parameter approach and contains a finite number of displacement chambers. This is a look inside the chamber element, and these icons are representing the equations I have already explained. The models and their interactions are controlled by a graphical user interface. As we can see, there are different areas to define the inputs and to visualize the output of the models. All essential pre- and post-processing operations can be performed out of this interface. For the purpose of validating the models, we considered these reference bumps. They are completely different as concerns the dimensions and the operating conditions. For experimental test, particular test rigs have been developed and built up at MAGNA Powertrain, and so we took advantage of measurements which were already existing. Here we see the validation of the steady-state pump operation. We consider two different tolerance settings. It is a sim-min pump with minimum clearance for tip and lateral clearance, and a sim-max, the maximum clearance pump. Here we see some more dynamic results for flow and pressure ripple for two different pump tolerance settings and a comparison with the corresponding experimental results. As already mentioned, the developed modeling approach can easily be integrated into the simulation of a complete hydraulic circuit. As an example, I want to show you how this has been realized for an electrohydraulic actuated coupling comprising models for the electric and control system, the hydraulic system, which includes the developed pump model, and the mechanical system. This enables us to predict the system behavior in automotive driving cycle simulations. As an example, we see the accumulated number of pump shaft revolutions for two different pump types and two different tolerance settings. And in that way, pump tolerance studies can be performed and the impact on the overall system behavior can be analyzed. In particular, the results shown in the table are used for an accurate evaluation of different pump design concepts concerning the prediction of system efficiency and wear of components. For example, the evaluation of lifetime of the electric motor bushings or the bearings. As mentioned before, we have already extended the model with the CFD model. It allows to perform detailed analysis of the leakage flow in the lateral sealing gaps. It is a constant gap model and the mesh is generated for several angular positions. The figure is showing the pressure field in the lubricating gap. Here we see the stress distribution obtained with the finite element model. For usual automotive drivetrain applications with a pressure level up to 30 bar, the elastic deformations of the parts are not significant. But this model has also been used for calculating the geometry of the radial gaps due to the dip clearance, and we considered the outer rotor to housing clearance as well as the inner rotor to shaft clearance. And this allows us to have a detailed description of the geometry of the radial gap that is not assumed as constant in the model. Here we see the validation of the geometry of the radial gaps. Because of geometrical tolerances, the measured dip clearance is varying when considering different D's contacts when the gears are meshing. Let me come to the conclusion. As we have seen at the current stage of development, the model is already useful for concept considerations. There are models which are interacting in different domains, and the models are managed by a central and easy to handle graphical user interface. The modeling approach is generally suitable for all possible gearing pump geometries, and the pump model can easily be integrated into a complete hydraulic system simulation, as we have seen on the example of the electrohydraulic actuated coupling. And it shows great potential for comprehensive and bidirectional coupling of the specific models. And this brings me to our future activities. We will continue working on the CFD model to accurately consider leakage flow passes and viscous torque losses in the lateral sealing gaps between the two gears and the housing. And this will be presented at the AFK Symposium in Dresden in Germany next year. And we will also continue working on the coupling of the 3D models with the lumped parameter fluid dynamic model. Well, this was a brief insight in our research work. Thank you for your attention and feel free to contact me if you have any questions about our research activities.